In this video, we're going to be representing chemical reactions, and we're also going to look at Lavoisier's contribution to the law of conservation of mass. And this is our part 6 video inside chemistry, chapter 3. So let's get started with this video. So starting off, we're going to talk about chemical reaction representation. So chemical reactions are represented using symbols and also formulas similar to how mathematics uses symbols for numbers and operation. So inside of math, we use symbols such as division, multiplication, subtraction, addition. So similarly, inside of chemistry, inside of chemical reactions, we also can use symbols and formulas to enhance the understanding. So here's an example: reaction of hydrogen plus oxygen to form water. So in this case, we're using the symbols of plus, which represents hydrogen plus oxygen. And then we also have this arrow, which basically means equals to. So hydrogen plus oxygen is equals to water. So this way we can also use symbols and formulas inside of chemical reactions, just like how we use it inside of math. So moving on, now we're going to talk about chemical equation accuracy. So chemical equations must accurately reflect the laws and theories related to chemical reactions, such as the law of conservation of mass. And the law of conservation of mass was first developed by a French chemist named Antoine Lavoisier during the 18th century. Now we're going to talk about Lavoisier's contribution and what he did to the law of conservation of mass. So Lavoisier emphasized the importance of careful measurements for the mass of reactants and products. So what he basically did was that on one side he put reactants and the other side he put products, and then he was the one that determined that both of the masses should be equal. So his observations led to him to generalize that the law of conservation of mass states that the total mass of the reacting substances, which is the reactants, is equal to the total mass of the resulting products. So basically what he said is that the mass of the reactants has to be equal to the product. So everything should be equal inside of the equation. And now we're going to talk about the closed system versus the open system and how that can relate to the law of conservation of mass. So in an open system, if we can look at this picture here, this one is an open system. So we can see that there is no lid or no covering on top, and it's open, so air can come in and go out. So inside of this open system, substances can enter or exit, making it difficult to demonstrate mass conservation inside of a reaction. And Lavoisier's experiments were conducted in closed systems which do not allow exchange of matter between the system and its surroundings, thereby illustrating the conservation of mass. So what we're seeing here is that in open systems, if it's open, then that means oxygen or anything else that's contaminated inside of the air can come and react with this. And once it reacts with that, then that means the mass of the product is going to be higher than what it was in the reactant. But Lavoisier, what he did was on every single experiment, he did it inside of a closed container. So when it's closed, then there's no way that air or anything from the environment can come in and actually affect the mass. So making sure, basically, if you're trying to create an observation or experiment, make sure you have a closed system in order to get the most accurate results. So now moving on, we're going to talk about writing balanced chemical equations. So the simplest form of representing a chemical reaction is a word equation that lists the reactants and products in words. So for example, as we talked about this before, hydrogen plus oxygen is equal to water. So this is a word equation where we have hydrogen plus oxygen as the reactants and then water as a product. So moving on, now we can also add symbols inside of our word equations. So inside of this word equation, there's multiple different symbols that we can find. One of them is the plus sign, which means reacts with. So one type of element reacts with another. And then there's also an arrow, which means to reduce. So if we look at this picture here, we can see that hydrogen plus oxygen, one of the symbols is the plus sign, which means hydrogen is reacting with oxygen or oxygen is reacting with hydrogen. And then this arrow means both of these, hydrogen plus oxygen, are producing water. And then reactants are placed on the left side of the arrow while products are on the right side. So you're always going to find the reactants that make up the product on the left side, and then the product itself will be on the right side. So now we're going to talk about the importance of balancing. So word equations can be represented by chemical formulas and also by symbols. So before, what we had was we wrote hydrogen by itself, just the word hydrogen, plus oxygen and spelled it out, is equal to water. So instead, what we're doing now is we're replacing that with the actual chemical formula and symbols. So hydrogen, which hydrogen gas by itself is H2 plus oxygen gas O2 is equal to H2O. So this is how we can just replace the word equation with a chemical formula and also symbols. And this is also the bare bones representation of a word equation, and it's called the skeleton equation. So basically, a skeleton equation is where you exactly just replace the word equation with the chemical formulas. And in this case, this is not balanced. And we're going to look at how we can balance this in the upcoming slides. And the chemical equation must be balanced, as we said, to obey the law of conservation of mass. So in this case, the reason why this is not balanced is if we look on the left side, we have to look at the number of atoms on both sides. They have to be equal for the law to be accurate. So if we look at the left side, we can see that there's 2 hydrogen atoms, and then on the right side, on the product, there's also 2 hydrogen atoms. So that clarifies, and that's fine. So that means those are balanced. But in this case, on the left side, on the reactant side, there's 2 oxygen atoms, but on the right side, there's only 1. So in this case, it's not balanced, and we're going to look at how we can do this in the next slide. So in the equation example, as we said before in the previous slide, the equation H2 plus O2 is equal to H2O is not balanced because it does not have an equal number of oxygen atoms on both sides. So in order to balance this, this is how it would look like. So in this case, what we're doing is, since there wasn't the same number of oxygen, we're going to add a coefficient of 2. So once we add a coefficient of 2, now we have 2 oxygens. So oxygens are now balanced. But since we added a coefficient of 2, then that means this hydrogen has 4 atoms now. So in order to balance it on the left side, we just add a coefficient of 2 here. So now we have 4 hydrogens plus 2 oxygens, and then on the right side we also have 4 hydrogens plus 2 oxygens. So this is how you can balance equations. And now we're going to talk about indicating the states of matter. So states of matter are indicated next to each chemical formula in the equation using abbreviations as shown in the table. So these are the different types of abbreviations and states that a formula can have. So if we look at the first one, there is a solid, which is represented as S. There's liquid, which is represented as L. There's gas, represented as G. And aqueous, which means it can be dissolved in water, and that's represented as AQ. So in this case, if we were to do our example from the previous slide, the hydrogen gas would be represented as G. The oxygen gas would be represented as G again, and then our water would be represented as L. So this is also how you can indicate states of matter, and it's also really important to do this as well. And now we're going to talk about the difference between endothermic and also exothermic reactions. So in endothermic reactions, we know that energy is absorbed and it's represented as a reactant. So inside of endothermic reactions and inside of the chemical formula, whenever we see it, we're always going to add thermal energy to the reactant side. So for this example, we have copper oxide plus thermal energy would make copper plus oxygen. So in this case, what we're doing is in endothermic, it's absorbing energy, so that's why it is on the reactant side. So the decomposition of copper oxide into copper and oxygen is endothermic, and the equation shows energy on the reactant side. So whenever you see energy on the reactant side, then you know that it's going to be an endothermic reaction. And now for exothermic reaction, it's exactly the opposite. So energy, we know that in exothermic reactions, energy is released, and it's often represented as a product of the reaction. And since the energy is often produced by the reaction, that's why we have it on the product side. So whenever you see thermal energy on the product side, then you know it's an exothermic reaction. So in this example, the reaction between sulfuric acid and sodium hydroxide form water, sodium sulfate, and also thermal energy. And this is exothermic as the equation shows energy as a product inside of the product section. So this is exothermic and endothermic reactions inside of a chemical equation. And that summarizes everything for this video. So thank you so much for watching from Try to Be Useful, and we'll see you in our next chemistry video.